Welcome to this next lecture on advanced reaction engineering. In the lecture so far, we have looked at real life reactors, we have looked at enthalpy effects, what happens when reactions are exothermic, and we have also seen how to characterize and how to analyze reactors with the help of residence time distribution when when the flow pattern or when the reactors don't behave like an idealized reactor of well mixed and plug flow. We are going to shift gears now. We are going to start looking at heterogeneous reactions. So let me just first of all uh, tell you where we are with respect to our syllabus. This is where we are in our syllabus. We are on the fourth part of our syllabus. Fourth, fifth, and sixth parts of our syllabus look at heterogeneous reactions. These three parts we had looked at were more or less looking at homogeneous reactions, or at least where we don't have to consider the second phase, where we could treat them like pseudo homogeneous. Now we are going to look at heterogeneous reactions. So the next part of the course, almost next half of the course, we are going to look at heterogeneous reactions. Just to help you revise and just to recap on what we have done so far, how do we estimate conversion for non-ideal reactors? What would be some other applications of these tracer techniques? We have seen tracer can be used for identifying or measuring residence time distribution in process equipment, but what could be other applications of tracer techniques? Find out more information about medical applications of tracers and radioisotopes for diagnostics and treatment. How are radiolabel compounds useful for finding reaction mechanisms? How are deuterated drugs useful for treatment? So this is just some background information. It's not very vital for our course, but these are some extra pieces of information that you might find useful and very interesting, that whatever concepts of RTD we have learned, similar concepts can be used for other applications and other fields. So this is where we are in our course. This is what we are going to do for the rest half of the course. We are going to look at heterogeneous reactions. In heterogeneous reactions, we are going to look at solid catalyzed reactions and non-catalyzed or homogeneously catalyzed reactions. Okay. In the solid catalyzed reactions, we are going to look at single fluid phase reactions. Means it is a solid catalyzed reaction, but it is catalyzed by solid particles, and the reaction is happening on the catalyst surface, but there is only one fluid phase. So it could be gas solid or liquid solid reaction. So just to give you an example, gas solid, for example, you are doing FCC cracking. So fluidized catalytic cracking for cracking of heavy compound like C20 plus or C18 C20 plus compounds in refineries. So they are vaporized and they are in the vapor space or vapor phase or gas phase, and the solid acts as a catalyst and to crack these molecules into gasoline fraction, and therefore we could get higher yield of petrol and gasoline fractions. So these are called as gas solid reactions. You might have liquid solid reactions as well. Say for example, there is any um, uh, liquid phase reactant, and the liquid phase reactants are catalyzed by solid particles. Just to give you an example, say for example glycerol. So glycerol is a waste product that we get, or a byproduct, we should not call it waste product, is a byproduct that we get from transesterification when you make biodiesel. So this glycerol is in the liquid phase, and we can add a value to that glycerol by reacting that glycerol with the help of a solid catalyst to make value added chemicals. So these are some of the places where we have liquid solid kind of reactions. Solid catalyzed reactions could also be fluid reactions. So for example, you could have a reaction between a gas and a liquid which is catalyzed by solid particles. So for example, you might think about hydrogenation of oil or hydrogenation of nitrobenzene. So hydrogen is in the vapor phase or gas phase, nitrobenzene or oil is in the liquid phase, and this reaction, hydrogenation of the double bonds in the oil, is catalyzed by solid catalyst. So platinum on carbon or palladium on carbon, those kinds of catalysts are used for hydrogenation reactions. So you could have solid catalyzed reactions but fluid reactions. You could have non-catalyzed or homogeneously catalyzed reactions take place by fluid reactions. For example, let me just give an example. Let's say absorption of ammonia in let's say ammonia in acidic solution. So HCl is used, aqueous HCl is used, or absorption of carbon dioxide using amine solutions. So carbon dioxide is in the gas phase, fluid phase. It reacts with amine in the liquid phase. Liquid phase is the second fluid phase. But this reaction between carbon dioxide and amine is an acid-base kind of reaction. It is not a catalyzed reaction. So this reaction is happening across two different phases, gas and liquid. Some component from gas reacts with some component in the liquid. The reaction is happening in one of the phases, in this particular case the liquid phase, but it's a non-catalyzed reaction. Okay? Or you could have a homogeneously catalyzed reaction. So for example, you might think of enzymes which act as catalysts for variety of biotransformation reactions. So these are reactions which could be having oxygen being transferred from gas to liquid. In the liquid phase we could have enzymes where reactions can take place, and therefore these are fluid reactions, and enzyme is a homogeneous material inside the fluid phase, liquid phase, aqueous phase. So they could be homogeneously catalyzed fluid reactions, right? So these are fluid reactions which are non-catalyzed or homogeneously catalyzed. Or you could have fluid solid reactions which are non-catalyzed. So for example, reaction between a fluid gas and a solid, say carbon is in the solid form and we have oxygen in the air. So we could have a reaction between oxygen and carbon in the solid phase, gas phase oxygen and solid phase carbon, combustion reaction. So fluidized bed combustion or fluidized bed boilers, which are used for generating steam in power plants and so on and so forth. So we are not going to look at these fluid solid reactions. You have done some of these things in your undergraduate course. If many of you have difficulties, then we can talk about them, but we are in general going to look at solid catalyzed reactions, fluid phase reaction, single fluid phase reaction. So either gas solid catalyzed reaction or liquid solid catalyzed reaction. And then we are going to look at fluid reactions which are non-catalyzed or homogeneously catalyzed, right? These are the two things that we are going to do in the subsequent portion of our course. Besides whatever example I have given just now, try to identify from literature or from your past experience or from your past courses some of the reactions that you have come across in each of these categories. Okay, so that's a homework for you, so that just you can better appreciate what is going to come and how ubiquitous or how useful this part of the portion is, because these reactions are very common, and in industrial scale or in industrial reactors you don't come across non-catalyzed or you don't come across homogeneously catalyzed reaction that much. You very often come across solid catalyzed reaction. So this is a very important part of our syllabus. So think about a solid catalyzed single fluid phase reaction. So imagine that this is our catalyst and there is a fluid phase reactant. So on this catalyst, so this catalyst is actually consists of, usually or most of the time, this the catalyst consists of two things. One is the support and second is the active site on which the reaction occurs. For example, if it's a hydrogenation reaction catalyzed by palladium on carbon or platinum on carbon, this carbon is merely acting as a solid support, and platinum clusters of platinum metal are at various locations on the catalyst surface, and these clusters of platinum metal act as active site. So these active sites catalyze a particular type of reaction. So for example, active site could be a noble metal like platinum or palladium. Active site could be a acidic site. You would have a acid. So for example, if it's a zeolite, the zeolite structure is the support, but in that structure there are acidic sites because of the aluminium present in the zeolite matrix, which has a unbalanced, or which has valency 3 in a silicon matrix. So that leaves a positive charge which acts like a acidic site. So these sites are very specific to the reaction, and a particular reaction will require a certain catalytic active site. So only certain kinds of active sites will catalyze certain kinds of reactions. Concentration and nature of these sites could be uniform. So for example, these are all uniform sites. Uniform in the sense the rate at which reactant reacts on each of these is the same. It is just a depiction. It's not necessary that they have to be same. All I'm trying to say is that the catalyst sites could be uniform in terms of deposition on the support. They are uniformly distributed, or they could be non-uniformly distributed, or there could be a distribution of activity of that particular active site. So for example, one active site may be very active for reaction, another site could be less active. So it could be, for example, if it's a palladium or a platinum catalyzed reaction, the size of the palladium cluster or platinum cluster decides the activity of those reactions. So you could have different sizes of clusters on, let's say, carbon support, and then because the sizes are different, they would react to different extent. Sometimes these catalyst sites are single or dual. So for example, you could have say single means you could have a platinum on a carbon. It's a single site. It's only going to catalyze hydrogenation, dehydrogenation, those kinds of reaction. Or it could be an acidic site which is catalyzing Friedel-Crafts alkylation kind of reactions. Or sometimes you might have dual sites. So you could have a noble metal as well as an acidic site. So you could have a platinum on alumina. So it might allow you to do isomerization and dehydrogenation or hydrogenation. So for example, in the refinery, these kinds of things are very much required. Two types of sites, that's why it's called as dual sites. Two types of sites are present, and both types of sites are required for reaction to take place. And the reason that some of these things act as catalyst, some of these metals, transition metals, act as catalyst is because on the surface they have unbalanced forces or unbalanced bonds which help them to bond with the reactants from the gas phase. And sometimes the support is just merely a phase which is allowing distribution of sites, or sometimes this support may also play an active role. So in say platinum or on alumina, platinum is an active site, but alumina also has a when alumina is used, it also acts as a acidic medium and allows some of these reactions to take place better. So the role of support and the active site, it is sometimes synergistic and gives you a very high rate of reaction. So this is actually how reactions take place on the surface of solid catalyst. So if you think about, let's say, any reaction that you have seen, say for example ammonia reaction, ammonia, nitrogen and hydrogen gas come in, and there is an iron catalyst that is inside the reactor. Or ethylene oxide, ethylene and oxygen come, they react on this silver catalyst. So it's typically a multi-tubular reactor. Inside the tube we have the catalyst, and the oxygen and ethylene mixture flows through this catalyst and it reacts, and the heat is removed from the shell side or gap between the two tubes. So if you look at any tube here and any inside the tube, you will find different catalyst particles or pellets that are kept in this tube. And if you look at one of this catalyst pellet into closer, you might find that this is a pellet and this catalyst has pores inside, and these pores inside these pores there are active sites. So these blue stars are these active sites. So these active sites are distributed in this catalyst pore, and then when the reactant flows, then the reactant goes through this catalyst pore and it reacts at these active sites. Okay, that's how these reactions occur, and whatever product is formed from that active site, it again goes back and desorbs and then goes along with the gas phase. So if you think about, let's say these active sites are silver clusters in ethylene oxide manufacture, you have ethylene and oxygen going, ethylene and oxygen gas molecules diffuse inside, they go towards this, let's say, active site silver center where reaction occurs, ethylene oxide is formed, ethylene oxide diffuses back out and then goes along with the gas. So these are how this is how actually reactions happen, and the porous nature of the catalyst provides large surface area on which these active sites could be deposited. So what I want you to do is draw concentration profiles. If I can break this down, or I can simplify this picture as, think about this as a this as one particle. So your particle is here, there is a pore, this particle has porous nature, so pores are all inside this particle, but outside this particle there is a fluid film, and beyond that is a bulk. So you must have seen film theory in your mass transfer. So in near the solid surface there is a fluid film, supposedly stagnant film, in which all the mass transfer resistance is situated, and then beyond that is a bulk. So what I would like you to do is draw a concentration profile of the reactant in the fluid bulk, fluid film, and how it will be, how the concentration will look like inside this porous solid. Okay, that's what I want you to do. Okay, and also write what are the steps involved. So pause, stop this video and do it for yourself. Only when you've done it, go ahead, pause. Okay, this is how our concentration profile will look like. All the mass transfer resistance is situated in the fluid film. So in the bulk there is no concentration difference, there is no concentration, it's all well mixed, so concentration is uniform. Let's say A is our reactant. So what we are plotting is concentration on this axis. Let me just draw the axis. What the axis that is drawn is, it is inherently assumed that this is the axis, y axis is our concentration of A, and this is a distance, it is some kind of distance away from the surface of the catalyst. So all the mass transfer resistance is situated in this fluid film. That's why there is a constant concentration, no mass transfer resistance. That's why it is called as bulk, fluid bulk. In the fluid film there is a mass transfer resistance, so concentration drops. Now once this reactant reaches this catalyst surface, then it diffuses inside and it also reacts. See, it is diffusing and it is also reacting. Say for example ethylene and oxygen, they are diffusing inside, but they are also reacting. Wherever there is an active site, they will also react. So diffusion and reaction happen simultaneously. As it is diffusing, it is reacting, therefore concentration will drop with respect to distance. Okay. Only when you are convinced, go ahead, pause otherwise. Here are the steps involved. First of all, this diffuse, the reactant has to diffuse from the external gas film to through the external film from gas bulk to the particle surface. So let's say it's a gas solid kind of reaction. So gas bulk to the surface of the particle, there is a mass transfer, diffusion. Okay. Then it has to diffuse through the pores and reach the particle site or reach the active site. When it is at the active site, this, let's say silver is the active site, ethylene and oxygen are our reactants in the gas phase. So they have to come together on the active site, then only that ethylene and oxygen will react with each other. So that happens in 3 steps. First of all, adsorption. Ethylene and oxygen, or one of them, adsorb on this active site, silver in this particular case. They react on the surface or react at the active site, and then the product that is formed, ethylene oxide, is desorbed from the active site back into the bulk. and then once it has back into the pore of the catalyst, and then once it is in the dissolved phase, in the gas phase inside the catalyst pore, that ethylene oxide has to diffuse back out into the towards the surface of the catalyst. And so once it is dissolved, once it is reached the surface of the catalyst, it has to diffuse back into the bulk. So if A is our reactant and R is our, let's say, product, or P is our product, can you draw a concentration profile of P now? I want you to draw a concentration profile of P now, product. How will that look like? So pause and do it for yourself. So P is formed here, and P is diffusing outside. So P will diffuse out. Formation and diffusion. Then it will diffuse through the external mass transfer film, and then it will be in the bulk. So the concentration difference of P between inside and outside, that's a driving force, because P is formed, therefore P concentration is higher inside the pore, so it diffuses out. So product diffuses out like this, and reactant diffuses in like this. So diffusion through the external film here, diffusion and reaction through the pore here, inside the pore at the active site, these three things happen. Then diffusion of product through the film, through the catalyst, this profile. Then diffusion through the external film, this profile. Okay. So these are the steps. This is how a catalyst allows reaction to happen. What we are going to do is, first of all, we are going to see some basic concepts related to gas solid reactions. Then we will look at more about these three steps: adsorption, chemical reaction, and desorption. These three things we are going to look at in detail in the next lecture. Okay. And this diffusion through the film and diffusion through the catalyst particle, this we will look at in another lecture, right? So this is what is going to come first, these three things, right? We are going to look at this first, and then we are going to look at this diffusion effects. In this lecture, we are going to look at some basic concepts that are involved. Okay? This is a basic concept, how things happen. In the subsequent lectures, now we'll start quantifying. We'll start quantifying these three steps: adsorption, reaction, and desorption. And in subsequent lecture, we'll characterize diffusion and reaction. This is how we are going to proceed. Okay. Just a little bit about reaction. How do I measure reaction, or how do I quantify rates of reaction? So when we had homogeneous reaction, how did we define rate? We defined rate as kilomoles reacted per unit time per unit volume. Correct? Now this rate I can define based on volume of catalyst. So rate would be kilomole per second per meter cube of catalyst. Or I can define rate based on per unit weight of catalyst, because we have to buy catalyst from some catalyst supplier. So we have to tell him, I want 100 kilograms of catalyst, right? That's how they will supply to us. So rate I could define based on kilomole per second per kg of catalyst weight. Or I have to put this catalyst inside a reactor. So what is important is rate of reaction per unit volume of reactor, right? So I could define rate based on kilomole per second per meter cube of reactor volume. In homogeneous reactor, this meter cube, whether it is of the liquid phase or whether it is in the reactor, they are one and the same, because it's a homogeneous, there's only one phase. But now this reactor is going to consist of catalyst as well as the gas phase, solid phase as well as gas phase, or fluid phase, liquid phase. So you have to think about it as what is the volume of the reactor. That's what is important. That's what we have to fabricate, and that's what we have to install in the plant. So we could define rate based on kilomole per second per meter cube of reactor volume. Actually, what is happening is on the catalyst active surface, active sites are there. So what is important for reaction to happen is how many kilomoles are per second are reacting per meter square of catalyst surface area. So that's how we could define rate based on any of these four categories or four ways of different defining. So if it's a first order reaction, then we can write rate on the basis of surface area. We could define it as a rate constant and Ca, and then Ks will have units of meter per second. See, if I define based on catalyst volume, then we can define Kv as just simply 1 per second, same way as a homogeneous reaction. If we are defining based on per unit catalyst weight, then it could be meter cube per second per kg of catalyst. Recall. So this is rate RAW. Let me explain. RAW is Kw into Ca. What is RAW? Kilomoles per second per kg of catalyst must be equal to Kw. Ca kilomoles per meter cube. So what are the units of Kw? Kilomole will cancel out. It is meter cube per second per kg of catalyst. Right? That's how the rate constant is defined based on catalyst volume. When rate is defined based on catalyst weight. If it's based on reactor volume, then it's like a homogeneous reaction. Rate is defined per second. Okay. So depending on how we want to define rate, based on what parameter we want to define rate, correspondingly the units of rate constant will be different. And then once I tell you the units of rate constant, it is obvious to you what kind of rate is being defined.
Okay, let's go forward. What we'll try to do now is try to interrelate all these different ways of expressing rates for a catalytic reaction. But before we start doing that, we will need some properties about the catalyst. For example, what is the surface area of the catalyst? How much catalyst is there in terms of weight? How many kgs of catalyst are there per unit volume of the catalyst or per unit volume of the reactor? So we'll need some of these catalyst properties. So let's first of all start looking at properties, then we will solve a problem. So first of all, we need to define density of the catalyst. So we are going to define density of the catalyst as rho p. It tells you how many kgs of catalyst is there per meter cube of the catalyst volume. Now if you imagine a reactor, let's say the reactor is like this. This reactor has a certain volume and the catalyst particles are, let's say, packed in that reactor. So now in terms of an actual commercial reactor, let's say, what is important is how many kgs of catalyst are there per unit reactor volume. So we call that as the bulk density of the catalyst. We denote that as rho b. Now as you can see that in this reactor only a fraction is occupied by the catalyst and the rest are void spaces between the catalyst particles, like these black ones are like the void spaces. So we need to define voidages in voidage in terms of what is the void volume. So we call that as epsilon, the bed voidage, and we call epsilon s as the volume fraction of the solids in the bed. So for example, now if you take 1 meter cube, let's say epsilon s is, let's say, 0.3. So epsilon voidage would be 1 minus 0.3 equal to 0.7. What does this mean? That if I take 1 meter cube of reactor volume, 0.3 meter cube would be catalyst and 0.7 meter cube would be my void spaces. Okay, is that clear? So very clearly we can define or we can relate the bulk density to the particle density. So for example, if the bulk density, let's say rho B, is 500 kgs per meter cube, what does that mean? 500 kgs of the catalyst are there per meter cube of the reactor. So if our basis is 1 meter cube of the reactor, how much catalyst we would have? We would have 500 kgs of catalyst. Okay, now this 500 kgs of catalyst, how much is the actual volume occupied by the catalyst? It's only 0.3 meter cube of the catalyst. So what is the particle density? What is the density of the catalyst? It would be 500 kgs divided by 0.3 meter cube of catalyst volume. Right? Is that okay? So what this means is that the rho B and rho P are related by what is the solid fraction. So rho B divided by epsilon S would be rho P, or rho P multiplied by solid fraction solid fraction epsilon S would be the bulk density of the catalyst. Okay. Another thing that is very important, because the catalyst is porous, catalyst has a surface area on which these active sites are there. So what is important is what is the surface area of the catalyst. So we define surface area of the catalyst is meter square per gram of catalyst. So remember, this surface area, it is not just the external surface area of this catalyst pellet. It is the surface area external plus internal, the pore surface area, like this. And you will see that the pore surface area is much larger than the external surface area, right? So we need to define how much surface area is there per unit weight of catalyst. Typically it is defined in terms of the meter square per gram of the catalyst. Also things like adsorbents. So if you are dealing with activated carbon, something that is getting something is adsorbing some, let's say, impurity from some solution, you need to define how much surface area is there per unit weight of the adsorbent, let's say activated carbon. In this particular case, it is the catalytic reactions that we are looking at. Now, many times, let's say for example, hydrogenation reactions, the entire surface area of the catalyst is not active. The catalyst is offering surface area only as a support to accommodate the active sites. So for example, if it's, let's say, a palladium on carbon or platinum on carbon, the carbon is actually acting as a support and the palladium metal is actually acting as the catalyst, for example, for hydrogenation reaction. So what we need, so imagine these blue things are like your blue stars are like your palladium metals, palladium metal sites on which the reaction occurs. So what is important is how much loading of the active material is there per gram of the catalyst. So typically it is defined in terms of the percentage. So typically the platinum loading or palladium loading could be 1 weight %. That means if I take 100 grams of the catalyst, 1 gram would be the active metal, palladium or platinum, depending on whatever the case is. Now what we need to do is, using these properties of the catalyst, we'll try to relate the different kinds of rates. Okay, I've just given you some formulae, but we will actually do a problem and come back to these formulae, and we'll see how these formulae come about. So don't mug up these formulae. We don't mug up anything. We try to look at everything right from fundamental principles. We try to derive everything that is required. So here is a problem. So imagine that there is a vapor phase hydrogenation reaction. Let's say for example, hydrogenation of nitrobenzene. Typically it is carried out in a vapor phase. So let's say it is carried out in presence of 1 weight %, 1 weight % platinum on carbon catalyst. So if I define rate based on the reactor volume, so I know the reactor volume, let's say it's an industrial reactor, I know the reactor volume and I know how many kilomoles per second are reacting. So let's say 0.1 kilomoles per second are reacting, and I've given you some catalyst properties, rho B, rho P, surface area, I want you to calculate the rate of reaction in different sets of units, and I would also like you to calculate the turnover frequency. Okay, so do this problem based on the definitions that um, we have defined here. Okay, stop the video, do these calculations for yourself, and once you have done it, then you can go forward and check whether your answer is right or wrong. Okay, stop the video. Okay, so I'm assuming now that you have done these calculations and you are checking your answer. So here is the solution. So what is this RA now? This RA is the rate per unit reactor volume. That means in terms of our nomenclature, it is this RA. Right? Now suppose I want to calculate all these other things. I want you to calculate RAS, RAV, RAW. Right? I would like you to calculate RAS. So what we are saying, calculate RAS, RAV, RAW. This is what I want you to calculate. Okay, and also the turnover frequency. All right, now how do I calculate? This is our RA. RA is 0.1 kilomoles per second per meter cube of catalyst. Oh, sorry, not catalyst. RA is per unit reactor volume. Now suppose I want RAS. What is RAS? What is RAS? Try to recall. RAS is well, let's take RAV first. Okay, RAV, that's easier. What is RAV? It is kilomoles per second per meter cube of catalyst volume. Okay. I have this RA is equal to 0.1 kilomole per second per meter cube of the reactor volume. Suppose I multiply this 0.1 kilomole per second per meter cube of reactor volume. Suppose I multiply this by reactor volume divided by catalyst volume. Can I do that? Okay. Then this reactor volume would get cancelled out, and I will have rate in terms of kilomole per second per meter cube of catalyst volume. Do you see that? So what I will need to do, I will need to take 0.1 multiplied by what is now the reciprocal of this, reactor volume and catalyst volume. Catalyst volume per reactor volume. Catalyst volume per reactor volume is nothing but epsilon S. So what is epsilon S? Epsilon S is 1 divided by, what is epsilon S? Oh, now we need epsilon S, right? Now how do you get epsilon S? We have rho P and rho B. How are they related? Let's go back. How are they related? Rho P and rho B are related like this, isn't it? So epsilon S would be rho B divided by rho P. So epsilon S would be rho B is 600 and rho P 1100. Okay, so this is 600 divided by 1100. Just do this, just make sure that you are getting the same answer. Epsilon S would be, that is 6 by 11, so I will just say 0.545. so this would be 0.1 divided by 0.4545. how much is that? So 0.1 divided by 0.545. how much is that? That's 0.1834. right? Do you realize what we have done? 0.1834. This 0.1834 is kilomoles per second per catalyst volume, right? So how have we got that? RA we have divided by epsilon S, that has given us RAV. Okay, or RAV multiplied by epsilon S would be our RA. Do you agree with that? Yes. This is what we had written. Where did we go? RAV, yeah, RA and RAV. This is how we have related. Okay, so just see that. Let's go forward, then you can come back. Now, so we have got RAV now. So RAV, this is our RAV. Okay, now how do I go forward? RAV, suppose I want RAW. What is RAW? Kilomoles per second per kg of catalyst, isn't it? RAV, this is 0.1 kilomole per second per meter cube of catalyst volume. Oops, I should say meter cube. Okay, suppose I multiply this 0.1 by kg by meter, I multiply it by meter cube of catalyst and divide by kg of catalyst, right? Then what will happen? Then this meter cube of catalyst would cancel out. Then I would have 0.1 multiplied by, I have to multiply by this number, kgs of catalyst per meter cube of catalyst volume. What is that? That is nothing but 1 by density of the catalyst particle, 1100, 1 by 1100. So this would be now my RAW. This would be, what is this now in terms of, just calculate point, oh sorry, this was now 0.1834. you see, it was 0.1834, not 0.1 here, it was 0.1834. let's let's do it again, just so that everybody is comfortable. What do we have? We have RAV, this is 0.1834 kilomoles of the reacted per second per meter cube of catalyst volume. If I multiply this by meter cube of catalyst divided by kgs of catalyst, what will I get? This would cancel out, this would cancel out. So I will get kilomoles per second per kg of catalyst. That's what I want. That's my RAW, isn't it? So this would be now 0.1834 multiplied by this number, meter cube of catalyst per kg of catalyst. That's just the reciprocal of rho p, isn't it? So this is 0.1834 divided by 1100. How much is that? 0.1834 divided by 1100. Somebody calculate. This is 1.67, let's say 1.67 into 10 raised to minus 4 kilomoles per second per kg of catalyst. That's what we wanted. That's what we wanted. RAW, isn't it? So do you see how we have got RAW? RAW would be RAV divided by rho p. Isn't that what we had? Aren't they related? Isn't this what you are seeing? RAV and RAW. This is what we are trying to relate. Okay, let's go forward. Suppose I want now RAS. What is RAS? What is RAS? RAS is kilomoles per second per meter square of catalyst surface area. How will I get that? I have 0.1834 into divided by 1100. So I have this number 1.67 into 10 raised to minus 4. This is kilomoles per second per kg of catalyst, isn't it? Suppose I multiply this by meter square of surface area and kg of catalyst. Then this kg would cancel out and we would get meter square kilomoles per second per meter square of surface area. So you see, what is the surface area? Surface area is 100 meter square per gram. So this would be 100 multiplied by 1000 meter square per kg, isn't it? So I will take this 1.67 into 10 raised to minus 4 multiplied by kg of catalyst per meter square. This is nothing but reciprocal of 100 into 1000. Do you agree with that? So this would be 1.67 into 10 raised to minus 4, 10 raised to minus 7 and 10 raised to minus 9. This would be 1.67 into 10 raised to minus 9 kilomoles per meter square of surface area, or per meter square of the catalyst. We don't say per meter square of surface area of catalyst, we just say per meter square of catalyst or surface area of catalyst per unit time. The time unit is always there. Is this not, this is our now RAS, isn't it? Do you see that? So how have we got RAS? We have got RAS by using RAW, and we have divided by the surface area 100 meter square, but actually it is, because surface area is defined per gram and RAW we have defined it per unit kg, so I will have to take 1000 multiplied by S, or RAW would be 1000 into S into RAS, right? Do you see that? And that's how we have been able to interconvert one into the other, right? All these unit conversions, they are here. Now you look at this slide, pause and look at this slide in view of what we have done here. Okay, one last thing that we need to do now. What is that? Our turnover frequency. So let's look at that now. Turnover frequency. What is our turnover frequency? What is our definition? How did we define that? Well, let's look at that here. Where did we define that? Yes, turnover frequency, number of moles reacted per unit time per unit mole of the active substance. Okay, so it is kilomoles reacted per unit time per kilomole of active substance. In this particular case, what is the active substance? It is platinum. Per kilomole of the active surface, which means platinum. Okay, or we could define in terms of gram moles per gram mole, right? That's our choice how we are defining. It is the same, gram mole per gram mole or kilomole per kilomole, it is the same. The turnover frequency has only units of 1 per second. Okay, so what have we got? We had got this RAW, right? So RAW, what was that? It was 1.67 into 10 raised to minus 4 kilomoles per second per kg of catalyst. Okay, but 1 kg of catalyst, it is only going to contain 1% platinum, right? So I want this kilomoles of platinum, but let's do it per kg of platinum. So if I multiply this by kg of platinum and kg of catalyst, right? So what would that be? This kg would cancel. Then I will have kilomole per second per kg of platinum. Do you see that? So if I take 1 kg of catalyst, I am going to get 1%. That means I am going to get 0.01 kgs of platinum, isn't it? So kgs of platinum per kg of catalyst, what would that be? 1.67 into 10 raised to minus 4 is kilomole per second per kg of catalyst. I need to suppose I take 1 kg of catalyst, I have only 0.01 kgs, 1% of platinum, right? So that means this is 1.67 into 10 raised to minus 2 kgs, kilomoles per second per kg of platinum. Okay, now what is the atomic weight of platinum? Somebody just do Google. Okay, let me also do Google, find out what is the atomic weight of platinum. Let's do that. Platinum atomic weight. It's 195. Right, let's just double check. We have to run it for platinum. Yes, 195. So what have we got? We have got this 1.67 into 10 raised to minus 2. That's our kilomoles per second, kilomoles reacted per second per kg of platinum, right? So if I take this 1.67 into 10 raised to minus 2, if I multiply this, this is what? Kilomoles per second per kg of platinum. If I multiply this by kilomoles, if I multiply this by kg of platinum per kilomole of platinum, then this kg would cancel and I will have kilomoles reacted per second per, should write this properly, kilomole per second per kilomole of platinum, right? So if I take 1 kilomole of platinum, that is 195 kgs, right? How we used to convert units when we studied process calculations. So this would be 1.67 into 10 raised to minus 2 multiplied by 195. So 1.67 10 raised to minus 2 into 195. How much is that? This is 3.26 kilomoles per second per kilomole of platinum, isn't it? So that's our turnover frequency, 3.26. We don't write this kilomole reacted per second per unit kilomole of the active metal. We just say 1 per second. That's our turnover frequency. Okay, so what we have done is now we have related all these things into turnover frequency. So just pause, just do all these calculations yourself and make sure that you have completely understood. There is one more problem coming up. In that problem, I will give you the turnover frequency and I will give you the catalyst property and I will ask you to do all the other things. All right. Okay, so that will just take a pause and make sure that you have understood all these concepts properly.
Here is a small problem. Fischer-Tropsch synthesis is studied using a model reaction, carbon monoxide plus hydrogen giving you methane and water. Catalyst is 0.5 weight% ruthenium on supported on gamma alumina. This is a support. This is actually the active side, active metal. Dispersion of ruthenium was found to be 50% using H2 chemisorption data. So little bit about H2 chemisorption, you take this catalyst, allow hydrogen to get adsorbed, and from that hydrogen you see how much ruthenium is accessible on the surface. So just to take you back, our catalyst is supported on the active side. So this is the active side, this is the surface area. This surface area is what is accessible. Suppose ruthenium is there here inside the solid support. It is not accessible to the reactant. Or let's say this is a pore. Let's say this is our active side, which is on the outside of the surface area of the pore. If there is ruthenium inside, trapped here, right, then that ruthenium is not accessible. So the amount of ruthenium available on the surface for reaction divided by amount of ruthenium total taken, or in general any metal taken, is called as dispersion of the metal. So what this means is 50% is available for reaction and the turnover frequency is 0.044 second inverse. Calculate the rate of reaction in gram mole per second per gram of catalyst weight. Dispersion of metal is the fraction of the metal available, which means accessible on the surface for the reaction to take place. Okay. One of the ways is to measure it using hydrogen adsorption. We know exactly how much hydrogen is adsorbed per atom of ruthenium. That's in part of catalysis. Let's not worry about that just now. But the description I wanted you to understand, dispersion, because part of the ruthenium is accessible on the surface, partly it is not accessible. It may be inside the bulk. That's not useful. 50% is dispersion, means 50% is what is available of the total weight of ruthenium. Okay, so find the rate, solve it for yourself. Pause. Okay, so if I take basis as 1 gram of the total weight of catalyst, right? That's what I want. Okay. In this 1 gram, how much ruthenium we are going to have? 0.58%, means 0.005 grams of ruthenium metal. Out of this ruthenium metal, how much is accessible? 50%. So 0.0025 grams of ruthenium metal is available for reaction. What is the turnover frequency? 0.044 seconds. So I'll have to convert this into kilo atoms or kilomoles of ruthenium, if you like. So ruthenium atomic weight we will need. So this corresponds to 0.0025 divided by 101.07 is 2.43, 2.47 into 10 raised to minus 5 gram atoms of ruthenium. This will be, now rate of reaction would be 2.4735, 2.4735 10 raised to minus 5 multiplied by 0.004044 is equal to 1.088 into 10 raised to minus 6 gram moles per second per gram of catalyst. That's our basis. See, so that's how we can calculate. That's how this dispersion tells us what is the useful part of our catalyst. Okay. Let's go forward. Now, little bit about pore sizes. So this catalyst is porous. Just little bit about the pore sizes of the catalyst. Sometimes these catalysts are called as macroporous. Macroporous means pore sizes are more than 50 nanometers. Sometimes the catalyst pores are very small. These are called as microporous catalysts. Microporous means pore size is less than 2 nanometers. So if you think about a molecule, if you think about these are the reactant molecules, let's say 5 angstrom, 6 angstrom, 10 angstroms, it's 1 nanometer of that sort. In macroporous catalyst, the pore size is very large as compared to molecular size. So the diffusion that happens is almost like bulk diffusion. Whereas if it's a microporous catalyst, less than 2 nanometer means 20 angstroms, size of the molecule starts becoming comparable to the size of the pores. So these molecules are not free to diffuse. Their diffusivity is called as Knudsen diffusivity or restricted diffusion. Okay. The catalyst surface area is measured by nitrogen adsorption called as BET isotherm. Okay. We are not going to go into details of that, but just for your background information, you can always refer to books or search on the internet what is a BET isotherm, how do I measure surface area of catalyst. Now let's imagine what else is important is active sites, not just the total surface area. I told you about that. What also is important is dispersion and size of the active sites, not just that there are active sites, right? Okay. Little bit about this bulk diffusion, Knudsen diffusion or restricted diffusion. So if I think about liquid diffusion through pores, then effective diffusivity is related to the tortuosity, porosity, tortuosity, or two concepts, porosity and tortuosity. So imagine that there is a catalyst, porous catalyst like this. So you see, now this material has to diffuse like this. It is a tortuous path. So let's say if this distance is, let's say, 1 millimeter, catalyst particles, pore size, particle size, if you like. Now the material actually does not travel a straight distance 1 millimeter. The material is traveling, gas, whatever molecules are there, they are traveling like this. So they will travel more distance than what is actually the size of the pellet or size of the particle. So distance traveled by this particle depends on how tortuous the pores are. So for example, this molecule is traveling like this. So the distance actually traveled divided by the size of the particle is called as tortuosity. So tortuosity is always more than 1. And porosity is how much is the so if I take this as, let's say, surface of the catalyst, porosity, what is the area occupied by pores? So if catalyst is, let's say, 1 millimeter by 1 millimeter cross section, and area of these pores, ratio of the area of the pores to the area of the cross section of the catalyst is called as porosity. So we want porosity to be as high as possible. So lot of the catalyst is occupied by the pores, and we want tortuosity to be less. Then the diffusion will be fast, right? Tortuosity to be almost 1, right? But in practice, tortuosity is 2, 3, 4, 5. That high means that much more tortuous the path is. Okay. So if it is a liquid that is diffusing through the pores, then the effective diffusivity is related to the restrictive factor Kr. So this restrictive factor Kr is defined as 1 minus diameter of the molecule divided by diameter of the pore raised to 4. Let's not worry about where this comes from. We will do this in your later on course, membrane separation. So let's not worry about this just now. So the effective diffusivity is Kr into porosity divided by tortuosity into molecular diffusivity or bulk diffusivity. So you will see that if porosity is 1, so everything is occupied by pore, bulk diffusion and effective diffusivity will be same. If tortuosity is high, effective diffusivity is less. Molecules take tortuous path. That's why effective diffusivity is less. Okay. So let's say pore diameter is 3 nanometer. Reactant molecule has a diameter of 0.8 nanometer. Calculate Kr. So Kr would be 1 minus diameter of the molecule 0.8 divided by diameter of the pore 3 nanometer raised to 4. Okay. And then effective diffusivity would be Kr. So this is 1 minus 0.8 divided by 3 raised to 4 into epsilon porosity 0.5 into bulk diffusivity 10 raised to minus 9 meter square per second divided by tortuosity 3. This will be the effective diffusivity. You will see that this effective diffusivity is going to be less than the bulk diffusivity. The effective is less than the bulk molecular diffusivity. Bulk diffusivity, let's call it as bulk. Okay. If gas is diffusing, Knudsen diffusion, right? So this Knudsen diffusion is related to, it is for gas, so we are assuming kinetic theory of gases. So this Knudsen diffusivity is related to the pore size, velocity of the molecules divided by 3, and velocity of the molecules you can get from kinetic theory of gases. This velocity is 8 RT divided by pi m square root, and effective diffusivity is epsilon by tau 1 by di. Di is the bulk diffusivity, and dki means Knudsen diffusivity for ith molecule, ith species, if you want. So let's just calculate this. So pore size, let's say dp is 0.5 nanometers. 0.5 nanometers means 5 into 10 raised to minus 0.5 into 10 raised to minus 9 means 5 into 10 raised to minus 10 meters. Velocity of the molecule Vi is 8 R, take SI units, 8314 joules per kilomole Kelvin. Let's say water vapor is at 300 Kelvin, temperature is 300 Kelvin, divided by pi M molecular weight 18. 18 what? Kilograms per kilomole. Square root of this. So Kelvin will cancel, kilomole will cancel. Okay. Joules per kg. Joules per kg is nothing but meter square per second square. Square root of that. So you will get velocity in meter per second. So Knudsen diffusivity would be pore size 5 into 10 raised to minus 10 meters. Velocity in meters per second, whatever value we've got, divided by 3. It will be meter square per second. And then effective diffusivity will be 1 by di, bulk diffusivity. Let's say bulk diffusivity is 10 raised to minus 5. So effective diffusivity will be epsilon. Let's say epsilon is 0.5 divided by tortuosity 3, like earlier case. 1 divided by 1 by di, 1 by molecular diffusivity or bulk diffusivity 10 raised to minus 5, plus 1 by this Knudsen diffusivity. This what we calculate in terms of meter square per second. So that's how you will be able to calculate this Knudsen diffusivity. Just to make sure that you understand, this is the value that we put here, and then this whole value you calculate for yourself, and that is what we put here, Knudsen diffusivity. Okay. Let's go forward. What I want you to do now is plot. So these are our concentration profiles. Remember, this is our concentration profile. So it's like resistances in series. A is to diffuse from the bulk to the pore and react there. Now there are different processes, right? This is one process. Diffusion from the gas bulk through the fluid film. Diffusion inside the pore. Reaction. These are the 3 steps. Now these 3 steps happen together. Any one of them could be rate controlling, or all 3 of them could be rate controlling. Slowest step. What I want you to do is look at these 3 steps. What are the 3 steps? Let me write them again here. Right? 1. What are the 3 steps? 1. Diffusion through the film. 2. Diffusion in pores. 3. Reaction. These are the 3 steps. What I want to do in the next 3 slides is, this is the catalyst. This black area or the gray area is a catalyst. This outside dotted line is a fluid film. So this is a catalyst. This is the film. Okay. What I want you to do is draw a concentration profile of the reactant. Let's say A is our reactant in terms of Ca versus distance. First, in this particular case, I want you to draw a profile if the reaction is limited by diffusion through external film. This is the rate controlling step. Means what? This first step is the slowest step. These 2 steps are fast, very fast. So how will the concentration profile look like? This is the bulk. Draw it for yourself. Okay, then only go forward. This is how it will look like. Concentration of A in the bulk. As soon as it comes to surface, it is 0, because this is the slowest step. It reacts as soon, it diffuses very fast, reacts very fast. Imagine this as if you are sitting here, you are very hungry, and this A is food that is coming to you. If the rate at which food comes to you is very small through this external mass transfer, kitchen to your table, there will be nothing on the table because you will eat it very quickly. This is how the concentration profile will look like. Next case, again let me write the 3 steps. One is diffusion through the film. Second, diffusion through pores. Third, reaction. This is our bulk. I want you to draw concentration profile of reactant A. This is our film. This is our catalyst. Now what I want you to say is diffusion is limited, rate is limited by diffusion through the catalyst pore. Diffusion through the catalyst pore. External mass transfer, that means this is the slowest step. Reaction is fast. Diffusion is fast through the film. Draw the profile. Pause. This is how it will look like. There's no mass transfer resistance in the film. So whatever is the bulk concentration, same concentration will be there at the surface. And it reacts, it diffuses and reacts. So this will be zero, practically zero. It is reacting very, very fast. So Ca would be zero here if you like, at the center. Next, if intrinsic kinetics is limited, again let me write the steps. One is diffusion through film, diffusion through pore, and 3, reaction. Now reaction is the slowest step. This is fast. This is fast. This is bulk. This is film. This is catalyst. I want you to draw Ca as a function of distance. Do this for yourself. This is how it will look like. External mass transfer is not limiting, so bulk and surface concentration will be the same. Diffusion is very fast, so it will react, it will diffuse, but very little reaction will occur. So concentration will be the same throughout the catalyst particle. Okay, think about these things. We are going to need these things later on in all our classes. Okay, so we'll stop this class here. We are looking at chapter 10 of 4th edition of Fogler's book. So you can revise, read that chapter accordingly. We are going to stop this lecture here. Look at all the concepts, try to understand all the concepts that we have done in this lecture. Revise, solve and read that chapter. Okay, so we'll stop here this lecture. In the next class, what we are going to do is looking at the reactions per se, adsorption, reaction, and desorption on the catalyst surface. Okay, that's the next part of our lecture. Then we will do diffusion through the external film, diffusion through the pores. Okay, next part. So adsorption, reaction, desorption. That's going to be in our next lecture.